Hello friends, this is Dr. Sivanagaraju, Associate Professor, AC Department from IARE. Today we are going to discuss the detection of DSB SC signals by using coherent detection and Costas Loop. In previous topics we covered how to generate DSB SC. Now how to detect the DSB SC signals. Okay, so here firstly we're using this coherent detection technique. Okay, coming to the topic. So this is the coherent detector. This coherent detector having three modules. The first one is product modulator, and this product modulator which is going to giving a local oscillator, and we're having a low pass filter. So these are the main blocks what that coherent detector having. Okay, so S of T is the modulated signal, what we call the DSB SC wave, which is going to apply to this product modulator. We're going to giving this DSB wave signal to the product modulator, and another output for this product modulator, another input what you're giving the product modulator is C of T. There is a carrier signal that is generated by a local oscillator, and this carrier signal which can represent as AC cos 2 pi FCT of plus pi. Here the pi is the phase difference. Okay, and the output of this product modulator is V of T, and this V of T is again applied to the low pass filter. Finally we're getting the demodulated output. Already know that low pass filter characteristics, which allows that low frequency signal, and which alternates high frequency signals. Okay, so let us see how this is going on. So the modulated signal M of T is recovered from a DSB SC wave S of T by first multiplying S of T with a local generated carrier wave and then low pass filtering. So that is the what you get the output. So the product modulator output can be given as V of T, which is equal to S of T into cos 2 pi FCT plus pi. That means here that modulated signal DSB as a signal which is multiplied with this carrier signal C of T cos 2 pi FCT plus pi. So what is S of T? S of T is the modulated signal. So we're having AC cos 2 pi FCT and M of T. So this is our S of T. So here we're going to substitute this equation to S of T and V of T. V of T. So we are going to substituting, then we're getting cos terms. AC cos 2 pi FCT plus pi into cos 2 pi FCT. So these are the cos terms. Two cos terms is coming. So we can treat it as a cos A, cos B. So we know that trigonometric formula cos A cos B, which is equal to 1 by 2 of cos of A minus B plus 1 by 2 cos of A plus B. So again rearranging this equation by using this trigonometric functions, then we can write as V of T, which is equal to AC M of T by 2 cos pi plus AC M of T by 2 cos 4 pi CT plus pi. Here already we said after getting this V of t is going to apply to the low pass filter. So the low pass filter having the bandwidth is greater than WH and lower than 2 FC minus WH. So finally, the output of this low pass filter is just AC M of t by 2 cos pi. Why? In the second term, having 4 pi FC. 4 pi FC, second term. So this is a high frequency term. So this high frequency term is alternated by that low pass filter. So finally, you got V0 of t, which is equal to AC by 2 cos pi M of t. So here the pi is a phase difference. So when pi is equal to 0, there is no difference. What happens? There's a cos pi is 0. So pi is 0, cos 0 is 1. So finally V0 of t is equal to AC by 2 M of t. So our aim is to extract message signal from DSB SC. So it is fulfilled. You're getting M of t. Then AC by 2 is some amplitude, or we can call it as some scale factor, what is maybe. But V0 of t, which is directly proportional to M of t. So we recovered message signal. Okay. So this is the output of this coherent detector. Okay. Next, we are going to Costas loop. This Costas loop is a practical one, what we're using for detecting DSB SC waves. So here also we're having two product modulators. One is placed at upper channel and another is placed at lower channel. So these two channels we can call as in-phase channel and quadrature channels. And also having a VCO and phase discriminator, low pass filters, and some phase shifter also used. So VCO is voltage control oscillator. So this is the block diagram of Costas loop. Okay. So Costas loop is a method of obtaining a practical synchronous receiver system suitable for demodulating DSB SC waves. So this receiver consists of two coherent detectors supplied with the same input signal. For the input signal, AC cos 2 pi FCT M of t. So that is our S of t. But with individual local oscillator signals that are in phase and quadrature with respect to each other. Okay. So this is a description about that block diagram. And these two detectors are coupled together to form a negative feedback system designed in such a way as to maintain the local oscillator synchronous with the carrier. Synchronous with the carrier. So now the working operation of this Costas loop. When the local oscillator signal is of the same phase as the carrier wave, AC cos 2 pi FCT used to generate the incoming DSB SC wave. Under these conditions, the in-phase channel or simply I channel output maintains the desired demodulated signal M of t, whereas Q channel or quadrature channel output is 0. So the output of in-phase channel is 1 by 2 AC M of t cos pi. 1 by 2 AC M of t cos pi. So which is actual what you get in the coherent detector also same. Why? This Costas loop is nothing but the combining of two coherent detectors. So in phase or in the upper channel, getting the output as one coherent detector output. So that is V naught of I, which is equal to 1 by 2 AC m of t cos pi. Whenever the carrier is synchronized, that pi is equal to 0. There is no difference or no error. Then this phi is equal to 0. So when phi equal to 0, cos pi is equal to 1. Then the output of the in-phase channel is 1 by 2 AC m of t. That is this output which is directly proportional to m of t. Our aim is to detect message signal. And what about this lower channel or quadrature channel or Q channel? So in the Q channel, we're having this cos pi is changed to sin pi. Again, you can see this block diagram. The phase shifter is there, 90 degrees phase shift. So cos is changed as sin. Okay. So at the output, we are also having this V naught of Q, which is in terms of sin. But here the phi is 0, sin 0 is 0. So sin phi is 0 simply. So output of V naught Q or output of quadrature channel is simply 0. Okay. So this is the working operation of Costas loop. And the output of I and Q channels are combined in phase discriminator followed by a low pass filter, and a DC control signal is obtained that automatically corrects for local phase errors in the voltage control oscillator. That means these errors are corrected by this VCO. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.